Okay. Good morning, everyone. Welcome to the second day of Introduction to Fortran series. Thank you for joining the second day. I hope you had a good time last week and got the time to do some homework with the demo codes and the slides. And we are happy that you joined the second day as well. Yeah, I'm not going to repeat all the logistics from last time, but few important things. As you know, we are recording this event, but you can interact with during the exercise, demo code exercise, because I will be editing the videos after this event. So we will not publish any user interaction while publishing the video. So that will be removed from the videos. And as you know, we follow the code of conduct, Carpenter's code of conduct, which is actually having a friendly and a learning atmosphere, both for the instructors, instructor, coordinator, and also the learners. So we urge everyone to use the welcoming language and being respectful to each other. And this collaborative document Ole is sharing now is the one we will use for an interaction and asking questions. The best thing is that we can publish it, and your questions and the answers will remain there even after the course. So the last day one's Q&A is archived and linked to the collaborative document. If you want to go back sometime later, you can see that there. We go through the answers and fix some here and there, but it's all there. And also the video recording, you might have received an email before the end of the Friday or late night Friday, because I took some time to edit the videos. And I hope those who couldn't attend has the ability, time to watch the video. And we have these two icebreaker questions, and we would like to hear from you your answer. Which data format are you mostly using? And you can list the data format, NetCDF, HDF5, ASCII, or any kind of data sets you are using. And one more question, what was your first programming language? And probably you can elaborate a little bit, what do you like programming at the first time? And the second, and then there is a poll, which approach you prefer, a human approach or computer architecture approach? This was, we were discussing on day one. So just would be nice to know about what you prefer. And without much delay, I would give the dais to Ole, your instructor. Back to you, Ole.
Yeah, thank you. Thank you very much. Yeah, as we, first of all, welcome. As we, on the first day, we went through something about the variables and how you approach the storage, that you store your numbers in. There were two approaches: the human approach, that I need maybe 3 digits for an integer, 4 digits, 1 digit. Who knows? That's only you can know that. And then ask the computer to provide you with storage space for such a number. Same for the real number. How many decimals do I actually need? And how much exponent do I need to the range of the thing? And I see that most of you prefer the human approach, which is actually very good. Then later on, on the coming days, you will learn how to write a module that contain all of these for you. So you can just ask the computer to provide you with those and give them labels or names, which you can use later on in your program. But I see also from the programs languages that have been used, they are all high language, and of which Python is one of the most modern. Very good. I think we go right through it. Without further delay, we jump over here. Today there is more time for trying out the demos and exercises. So I really hope that you can set aside time to join me in running through a little more depth than last time. We had quite a lot of in material to convey last time, but there is still a few things to learn today. But hopefully I did see that for the formats and a few other things need to more practice than actually theoretical work, because they are more things that you're learning by doing than just planting an idea in your head. Yep. This is the book I put up last time, so I thought I might have a picture of it. I found it on my local library here. It should be available in the libraries on the other university. I think if you go to the Natural Science Library in Oslo, I think I have the only copy. But in other places, there might be a copy, and I'll put it back quite soon. But this is a very nice book. The more I read, the more I learn, because there are so many things I didn't know. So, yeah. Today's topic is also covering input and output in more detail, especially with formatting. Formatting is important to present the data in a readable way for the humans, and it's also how you read and write them on a file, especially reading data from a file. It can also be done in different ways. But the whole thing with this language is that you have print, which is printing to the terminal. Write, can you use terminal? If you give it number 6 or just an asterisk or star, it will automatically default to the terminal. So unit number 6 is the terminal. As I said in the first day, in number 5 is the keyboard or the card reader or whatever. And number 6 is for the terminal, which is your screen. So if I set the unit number to number 6, I use a format. A will go through all of the characters and such for the formats later on. Then I can call the first one to print to screen. I can just say format, just A, it has to be in parentheses, and of course it's a string, it has to be quoted. Then I say A, which is the format for a string, hello world, that will print hello world. If I then set a variable of a string type called format to the string parentheses around A, I can feed that into the write statement together with the unit number, and to write out it's the hello world string, and it will print hello world onto your screen. So there you can use format, the same type of format. They are identical for both print and write. To write to terminal using print, I use both approaches. There's not the only thing with print is that it's a slightly different syntax, and it's only printing to the screen. You can't redirect it, not easily at least. Write is a more universal one that can print to any kind of device of which the terminal or which the screen is only one of them. You can print to files, you can print to internal files, etc. So write is a more universal one and has a lot of options that you can use, like you could say the non-advance, so that it will not print a new line when it ends. Some of these things that are more versatile with both the read and the write statement, and we'll cover that later on. So a little bit more about, I can say the simple one is the first one, print hello world with the format, a string, hello world again. I can also have the format inline as a string into the write statement instead of using a variable. I can just give the string directly in line number 3. I can then declare a variable called form and set that to a string of format. So the I3, the X, A, and X, and F 5.2 is fed into the variable form, and then I write to the default, this star or asterisk is the default, which is the screen. Using of this format, then I put into to be written out as an option, as an input to write. 127 is an int, and then 3.3.14 as a floating point number. We'll go through more detail on this later, but the important message to take home here, as variables must match the format. And to make matters a bit worse, is that there is no compile error. It will become a runtime error. Your program will just probably crash or write out strange things, binary characters on the screen, which is not always a nice thing, or crap. So but if you're unlucky, you get crap. If you're unlucky, or depending on how you see it, lucky or not, the program will terminate, will abort. So variables must match the format. So be aware that you check that this thing happened. So a comprehensive list of the most common formats. There are a few more, but these are the most common. A is for text, character string. I is for integers. Here I put the number 3 after the I. I3 is with, well, it's a spelling mistake, but it doesn't matter, up to 3 digits. If you put in more, you either get you get asterisk printed out, so it doesn't make sense, or yeah. And then you need to change the number to accommodate for a larger number, which is related to how many numbers you have in your variable. Let's say if you have an int 8, which is 8-bit integer that can range up to 127, then you only need 3. If you have an int 16, you need 5 places, because it goes from plus and minus 32,635. So that shouldn't be too hard. If I say I6.4, that will yield leading zeros. We have an example of that. So if you put a dot after an I, because there normally that will be decimal. If you have an F or E, it will be decimal places. But if you say I6.4, that will yield leading zeros, which in some cases can be beneficial. Then we move to the next one. F is for float. We normally call it reals, floating point numbers. In this case, the F10.3 is for reals with total of 10 characters and 3 decimal places. So remember that this is for float with no exponent. So these numbers can become very large. They can have a lot of digits, which is, first of all, is hard to read, but in principle, these numbers are fixed. They have no exponent, so they will either be plus or minus. No, they will be plus or minus a lot of numbers with a few decimals, or .0000 and numbers. So they are decimals, normal decimals with no exponent. So be careful if you have numbers that are different in range using this decimal. But if you know that your numbers are a few numbers and a few decimal places, then the F is very good. You have to play around a little bit to see what you like, but F is for everyday numbers. Then we go to the E, scientific notation with decimals and an exponent. Here I asked for 12 spaces with 8 decimals. You need to accommodate for the fact that you have 2 or 3 numbers for the exponent and 1 for the e, signifying the exponent. So you need more room than just a couple of numbers for more than the decimals. So you need to accommodate for more width than you would expect if you were a floating point number. Then there is an extension to the E format, and I mixed capital and lowercase letters here, which is by choice, showing that it doesn't matter. You can take it, it's case insensitive. So engineering notation with decimals and exponent. Here I ask for a width of 10. No, width 10 with 2 decimal places. Engineering notation have normally from 1 to 3 digits left of the comma and an exponent. This is one way of seeing it. Some people prefer that. Then you have the scientific notation. I wonder if it should be ES and not ED. Sorry for that one. Scientific notations that will have only one number before the comma on left-hand side of the comma, and decimals and an exponent. So this is probably the most used. Then I make a bit more complicated format, the 3I4. If you put a 3 ahead of the format, it signifies how many of those you will use. So the 3I4 means that there are 3 integers to be printed, each with a width of up to 4 digits. The next one is something that is even more complicated. And in order to have a 5 tuple, you need to have 5 of the tuples in there. You need to have a parenthesis around it. Otherwise, it would just be 5 strings and a single float number. But since I want 5 of these, 5 tuples containing text and a float, I need to have a parenthesis around it. That means that there are 5 tuples, each containing a string and a floating point number with 0 decimals, but 3 places. Then the G format is a scientific format, which is a bit a human approach. It adapts itself to what looks nice for humans. If I say 3.4, it will print 3.4. If I feed in 3.4 e to the -7th, it will print in exponential form. So it's a bit more human format. The use is the format depending on the value of the number. So G can be a nice one if you don't prefer the scientific or engineering. Then there we have the L, which is a logical format. If you use L, it will print true or false. So it will say T or F if you use the format logical. This is a list of the most common ones for the number and text and logical. We have a little bit more formatting. An X will emit a space. A slash would emit a line feed. And SP is an interesting one. It will print a plus for positive numbers. Of course, negative will always have a negative, but it will emit a plus for the positive numbers. So if you to make 100% sure, you could combine this with the leading 0. So it will be plus 0, 0, 2, signifying a positive integer with the value of 2. Then it's a decimal symbol, which is an interesting one, because in the Norwegian setup, especially in spreadsheets, you see it that the comma is used as a decimal comma and not the dot. So in the English speaking world, they use dot as the decimal comma. In Norwegian, Swedish, and Danish, and Scandinavia, we are using the comma as a decimal comma. So you can actually set that in the format if you like to print out data readable for the for Scandinavian or Nordic countries. If you look on this book I just mentioned, there is a lot of other things, but these are the most common that you will come across and probably use. There are some tabulating and so on, and there are a few special things, but this is an introduction, is not going too deeply into the stuff. I have made a few. This is just a grep from the examples. I have some I call it format strings, and you can make it quite complicated. You can see I have 8 and I have a comma. You can actually put a string that to be printed inside the format statement. So this one will print commas around the numbers as such. And then you can say, you don't have to use comma between them. Like in this first one, I say a comma 2x. You don't need a comma, but it's easier to read. So if you prefer to use a comma, please do. If you don't, then it's no need to do it. And like the last one, we have 10 strings and integers. The syntax again, print using the format string and the variables. The write is using a unit number, default one here, and the format equals the variable. And of course, there should be a parenthesis after here. Sorry for that. I thought I ran through most of the slides. Yeah, like this. Sorry for that. So there are other interesting things with this. This can be a bit tricky. We want to write things to a string. You see, I didn't put in any unit number here. I put a string instead of the unit number. This is referred to as something called an internal file. In C, it's an own function. It's sprintf to write to a string, but in Fortran you don't use a separate function. You use the same write, but instead of the unit number, you give it a string. So it actually writes to a variable. So in this case, the character variable or string variable characters with a length of something, which is called a string, would be written into the hello world string. So if you print out string later, it will contain hello world. But this is interesting because if I write the program and I don't know how many numbers to print, and I want them printed, let's say, on one line, I need to prepare a format at runtime. And that's not so easy, since we earlier saw that the formats are fixed at compile time. So then I can write the format into a format string with some numbers that are only known at runtime. I have an example of this, so we'll It's not as complicated as it sounds, but it's a bit complicated to explain it here. So if you ever come across internal file, this is just that you are writing to a variable. It can be internal file, could be any kind of variable that you can write into. You can have a double precision number and assign that and write that into hello world. But then you need to make it either formatted or unformatted. Otherwise, the number will be a string. If you write a double precision number in a formatted way, it will be in text. If you write it with unformatted, it will be only the 64 bits that you are stored in the variable. So it opened up a lot of interesting things that you can do. But I'm using internal file mostly for preparing format strings, which is bring us up to some of the examples. There are format, but I mentioned the last time about the construct of implied loop. Implied loop are an interesting concept because it's a very powerful tool, and it's a very, very simple loop that can help you assigning things, making vectors, printing. You'll see a few examples of the implied loop. So this is something that you should actually learn how to do. But I think we'll start with some examples, and I will shuffle around. I will start with the implied loop, and then we go through format and format 2. Format 2 is it's an example of internal files, etc. So I lost the line here. How is the fonts on Emacs? Is it too small or readable?
Readable for me. Ole, do you want to hide the slides or just the terminal?
No, I can make the Emacs bigger.
Yeah.
Because I deliberately made a workspace so that there was nothing of non-general interest on any of the screens I have before me. Because like being unlucky and having them at the most, etc. up here would be, so it doesn't really matter because I make sure that it wasn't a problem.
Yeah.
Are
you going to walk through this program?
Yeah, I'm going, and then we'll set aside a little bit of time so people can run them themselves. But we'll go through these three things with implied do loops and the 2 format one. Then all the participants can run themselves. Of course,
did we talk about use ISO Fortran environment and implicit none last time?
Yes, we covered ISO Fortran environment and implicit none. Yeah. Never leave home without it. Always use implicit none. We learned that from the mistakes with the spacecraft.
Yeah, I just want to repeat that because if there is someone who couldn't join last time.
Yeah. No, Fortran environment specify a little bit about the variables and a few other things. Implicit none means that any variable that isn't declared is declared nothing. So if you assign it, you'll get an error. I say declare an integer of the size 8 bits, which it runs from plus 127 to minus 128, or the opposite, minus 128 until plus 127. If you have anything bigger than that, it will fail. But this is small numbers, so it doesn't matter. The implied loop, I say print an I, comma, and I runs from 1 to 10. You can have 2 implied loops, I and j, and then I print 10 numbers of 3 digits each. If I have 3 digits in the number, there will be no space between the numbers. So you have to accommodate for that. and I plus j, which goes up to 20. Then I can have actually 3 uses of the loop counter with a single one. So we'll see how this works. This time I'm running on my own machine, but no, I can run on Saga, but I need to enlarge the font. Is it okay? Big enough?
Yes.
I have called for the module called GCC 12.2. I think you need a fairly recent GCC in order to run the examples, because we need to have support for the 2008 standard. So I'm not sure if anything laid earlier than 12 supported all of them. So start at 12.2, but I think 11 and 12 or 10 and 11 also support a lot of things in 2008, but I'm not 100% sure. So I have always tested by GCC 12.
If anyone downloaded or installed things on their laptop recently, that would be fine.
We compile. As I said last time, I'm lazy, and I just call a.out. So we get one implied loop. This is here. We print the default format. We print the I, and I round from 1 to 10. And we get 1 to 10. Cool. We go to 2 implied loops. We have, first of all, here I plus j, comma, for the first loop, parenthesis, end. Then we have another comma, and we place another loop, which is related to the left-hand side parenthesis, the outermost of those. So we get 2 loops outside of each other, nested loops, and we print 10 numbers on each line. And what we get 2 implied loops. For the first one, we get 1 to 11, which is I plus 1. 1 plus 1 is 2. 10 plus 1 is 11. That makes sense. And it goes all the way up to 11 plus. So 10 plus 10 is 20. And you can see the nice formatting, because when the 10i3 format, when you use this format, it will take numbers until 10 is reached. When you have exhausted the 10, it come to 10 and we exhaust this format, the write is finished and it emit a new line. So there is no need to call for a new line here. It will automatically emit a new line when these 10 numbers, when the format is filled, and then start again. And a nice trick. So I don't need to have a loop controlling an extra new line here. So I just print out 10 numbers and start putting in more numbers, and then there will be a new line, and the new name numbers will come on the next line. Hence the nice table. So this is something that's important to remember, that there is a new line emitted every time you have produced enough numbers to fill the format. We can go to the next one here. I prepared a line inline. I use print instead of write. I said I3, and then I use a comma and an X, comma again. Comma is not emitted because it's just separating the format, so it doesn't matter. You can have it or not. Your choice. And the X is emitting a space. And then I had to use I4. because I times I could be more than 99 or more than 100. So if I had in time 4 here, it will be less space. So I put in 4. And if you couldn't increase either, because then the variable j and I wasn't able to accommodate more than up to 127, since it's positive numbers. So this is a simple demonstration of how to use the implied loops when printing numbers. You can use it several other places too, but you can have 2 implied loops here, A and J. You can have more, and it's no end to it. You can use the numbers A, the variable here, in different time. You can just comma separate them. You can also call functions here, like taking the square root or the absolute value or whatever. If you put negative numbers here, could be an interesting exercise. From, let's say, -5 to 4. Counting 0, it would be 10. Of course. Of course it would work. Because this is on Saga. So, what I can do. Yeah, we'll see that they will come out in this way. So I deliberately put an X here to make sure that there is a space between the numbers. So this is the implied loop. I think you should keep one of these lines here lying around, so you never know when you're going to need such a thing, or make a directory in your home directory called F90 or F2008. Keep snippets of cool code that you need, and the implied loop is one of those you should keep. Anyway, we go to the next step. I'll leave you some time to run this yourself. Here I put in some helpful text in the comments. Here we put is the ubiquitous hello world, the different forms of it. Here I use a variable to have the format. We put in one string of new line and another string, so then the logical, it will print out the logical. I call the function trim, which is get rid of the blanks, because if you go up here and see, I put in the length of 60. So if I use 60 and didn't use the trim, it will be a lot of blanks, a lot of spaces, and that's not really needed. So I wanted to make it to look nicer, so I used trim to knock out all the spaces. We'll see when we're on it. Then we have an example of leading zeros. Integer with leading zeros. Then we have a slightly more complicated one. We have a string, 2 spaces, one integer, and one real. I here also use comma to separate them. Makes it easier to read. I give the byte numbers k, and x. K is an integer, X is a floating point number. Then we'll do some more. We not go, instead of using float, we use the exponent format. Then we explore the using of the G. Then we use the same, but G behave differently. And then even a bit more complicated again. And engineering format and science type. Here we have EN 10.2 and ES 10.2. So this is exploring a little bit of different formats that you can play around with, and we'll see what happens if we run. So we get hello world in different types, but this one is interesting. Here we have a slash, which is a line feed. That will give hello world if there are two strings, one called hello, one contain hello, the other string is world, and there's a one string, a new line, and one string. Then with two lines. Oh, nice. Then we have three strings, a logical, a space, and a logical. So why three? We have a string here called logical format. Then we have a string here, trim form, which is this one, trim for all the blanks, so we only get the string we put in. And then yet another string with the parentheses and comma. Things can be fairly complicated. There's no end to how complicated it can be. So sometimes you need to make this automatically, that use internal format and build the strings in a programmed way. And then now you have two constants, one constant called true and one constant called false. Of course, they could be logical variables containing true and false, but I just use some constant. Then we use the leading zeros as string, which is the format string. Here, it doesn't matter if we have a lot of blanks, because there is nothing to be printed right of that one, so we don't see the blanks. They are there, but we don't see them because we skip to the next line. Then we print out the leading zeros and minus 24. Again, we'll see. We have the logical format, true and false. Then we have the leading zeros, which uses 4 spaces here, 4, and a minus in the ahead of the zeros. Good. Then we have the numbers here. Well, here's something wrong. We know that K is 123. And I say 2x, so there are 2 blanks here. But I3 is using 3 spaces. So 123. Then there is no x here. Then there comes the next, 123. Then there is a comma here, so there's no space. Then the floating point number, 3.14, which I said here, is printed back to back. So all of these numbers are printed back to back. There are 2 ways of getting around this. We can increase the 3 to 5 or 4 or whatever, but it's a little bit unpredictable. A better way of doing it is to go to the next one, where I have said 2x, I3, 1x, I3, 1x, and so on. So I'm sure that whatever happened, even though if the number is not large enough, it will print asterisk, there will be a blank between them, which we see here, 123, space, space, and the exponent format. The E format normalizes the number, so they run from 0 to dot 0.99999. So there will always be a 0 here in the E format. Then we'll go to the more or less the same, except that we have the E again, but I also included the G format, the human approach format. That will give us the same, but the G format gives us 3.14, which is interesting because it's more or less the same as in floating point numbers, but during the next line, I multiply x by 10 to the minus 7. So the x is now a very small number. And then I get the same, but for the E format, I get the normalized number. And the G also give us the normalized number. So G, when the number needs an exponent, G will provide us with the normalized number like the E. So G is some mixture of F and G, F and E, Foxtrot or Echo, F and E. So it will always print a human readable format. Then there is those two new ones, scientific form and engineering form, which is the two last ones. Those are, here we can see the decimal problem. The float format will give us this. The engineering will give us 3 digits. It could be I don't think it's, I haven't tested, but I expect that they will not go to 1000. They will stop at 999 and then wrap to 1 again, so that you will just increase the exponent. I haven't tried it, but I expect so, since it's engineering format. But scientific format will be the format we'll normally like. So I generally prefer this one. This is how I do it in paper and pencil. But I always known that Fortran is by default doing this. But this engineering format or scientific formats are fairly new. I can't recall which standard they were introduced, but they are in the 2008 standard. So if you go with the 2008 and forward, it should be easy. And then, of course, GNU support this, and then most of the other commercial compilers all more or less have to follow the GNU. So a little bit about formats before we let you try. We have format 2. Same again, but this is a bit more tricky. Here I ask for, of course, never leave home without them. These two are mandatory. Should be so that if you were presenting a master and a doctoral thesis and somebody asked to see your Fortran program, if these were missing, you will go home and do your homework and come again. Try again. Next, nice try, but no close, but no cigar. This is really important. If it's anything you need to learn from these exercises, it's those 2 lines. Well, this line is it not. 16-bit, they run from 32,000 and so. 20-character long format string. But now we are dynamic formats. I call it advanced formatting and internal files, but yeah. We ask for a number. Of course, you see there is no test, so please do not give characters. I think we had a test for that last time. how you could do, or yeah. Here is the real tricky one. Since we don't know how many numbers we are going to print, we need to feed this into the format string. So I put in form here. Form is a character, a form is a string of length 20. First, I feed in this string. And then I put a parenthesis there for this is for the write statement. So the string to be made contains a string, an integer which has an unknown width, a new string. So what are we feeding in? We are feeding in a parenthesis, which is needed, an n containing how many numbers that we will use, how many you are asked to put in, then an I1 and an X. This is called an internal file. Format string now looks like, and then we print using it. We print, since we know the n is the number given up here, we can take power 2 of it with the format we just created. So the format we now created will now print out as many as we entered here. But yeah, we can try it because it's more pedagogic to. How many numbers? 4. Forget the other things, but look here now. Format string now looks like 4 I1.x. Which is right. We put in 4, we get the number 4 in there in the format string. We have an I1 and we have a space. Of course, there will be a space after the here, but it doesn't matter. And you see that there is not room enough for 10 or 16, sorry. So that's not good. But then again, if we said 2 here, we'll have the same problem with the larger number. If we have 100, it would still give us a problem here with the format. So we need to fix this once and for all. And how do we count the number of digits in a number? Well, we take the log 10. And since we know that we could have up to n times n, j times j, we know that we need to figure out the logarithm of 10 times n times n, log 10. We print that one. That comes to 1.2. But then again, log 100 is 2. But 100 has 3 numbers. So we need to add 1 to make sure that we are something just above 2. We could have 2, 3, or it doesn't matter, but 1 is enough. And then we call the ceiling function, which rounds up a floating point number to the nearest integer, rounding up. So that will be 2 in this case. 1.2 rounded up is 2. So k equals 2. Then we prepare a new format string where we have 2 numbers. And the new format string now look like 4, A2, and an X to have a space between the numbers. Then we write out the thing again, same thing, and we get 1, 4, 9, 16. So an exercise to play around with for you, probably not during the time to test these ones, but to play with it later, that if you enter a number like 25, it will wrap the line. You see? So an exercise would be to only emit 80 characters per line. So if you have a very, very big number, then it's more tricky than you think. So, and what happens if you enter 1,000? It goes haywire. There's a lot of strange things going on here. But this we covered last time, that some of these become negative. So that's why we had these bad accidents that we with the videos. I hope you all got time to see those 2 videos about what poor programming can kill people. But I think we'll set aside how much? 10 minutes and then 5 minutes Q&A and then a break. What do you think, Tanya?
Yeah, that maybe like 8 minutes and then 5 minutes Q&A.
Yeah. Okay.
Yeah.
You call the time.
Yeah, that you can try out these formatting programs. I would like to add something, but I'm not sure this is valid now also, because formatting compiler errors and runtime errors. When I was starting program with Fortran, I encountered a lot of compilation error as well as runtime error because of bad formatting. I forget parentheses, I forget commas.
If you forget parentheses and commas, the compiler will normally slap your fingers.
Yeah.
And that's a nice thing, because then then you get immediate response. Imagine now that you have written your climate code. After 7 days of compilation of computing, you get a format error at the end, a runtime error. So runtime errors are actually more painful than compile errors. So test your format strings and so on, or test your programs, because it's very, very bad to run for days and then your program abort at the printing out phase. So yes, we all have been there. So when I say you should avoid something, I've done that mistake myself.
Yeah, I just wanted to point out, since this course you made it, so everything is kind of perfect there. But when we start writing, these errors are, yeah, everyone comes meet some errors in some time. So that's not a issue. It happens to everyone.
But you never saw how many errors I got while writing these programs. It's a little bit trial and error also.
Yeah.
So, but I think it's important that I write the demos myself instead of copying. There's a couple of things I did copy, but then it's clearly stated in the text. Oh, print statement automatically provides spaces.
Yeah, I wrote the answer.
Yeah. Print is equivalent to units. Yeah.
Yeah, I thought that's the correct answer, right?
Yeah, I think that's, yeah. If you write free format, you leave it to the compiler and the runtime system to fix it. that should normally be quite nicely to use free format, but not always. I didn't say much about free format, but yes, free format is, if you don't care how it looks, then free format is okay. Free format is widely used when reading in, because you never know what the users are expected to input. Like numbers. Numbers could be very different. Numbers could be just numbers. It could be a decimal point. It could be an exponent. It could be a negative exponent. It could be a lot of strange things. And then if you use free format, then it's better.
One thing about this unit numbers, do we still have this default unit numbers 1, 2? Because that's also some error I come up when I was doing programming first time. I used the file numbers for file unit numbers 1 and 2, and I got the error. Now, after that, I always started off with number 10, after number 10. So I don't know if still it is.
I have been using unit number 2 for files for time, but you could be facing that they used the Fortran you used the C convention 0, 1, and 2. Because the C is using 0 for keyboard, 1 for terminal, and 2 for terminal, but the standard error device. So it could be, but then it could very well be that some unit numbers are already allocated. So yeah, that's a bit tricky, because you have to, there's no way that you can get the compiler to set the unit number for you. At least I don't know about it, but so you should pick one. But starting at 10 should be safe. Or 17.
Yeah.
Because 17 is the most random number. So my random number generator is very easy. Random, begin, return 17, end.
I'm just bringing this up because I want everyone to know that you will go through many errors when you start writing programs.
Yeah.
It's not fancy like what Ole shows here, because.
What does R8 mean? Yeah.
I
was is this one of the exercises today, or is this an older one? What does R8 mean? I can show that if I grep R8, I'm not sure if we have it. No.
Okay. What does starting?
Here. Here. We can copy this one into the collaborative document.
I think we have some yes from the poll, Ole. Do you want to take the question 5? If you want to ask question, you can ask it here. I will anyhow edit this part.
Yeah.
There is this question 5, the IO format here. Which code is this? How does that set a 1-digit length?
Yeah. The I0, it's a bit tricky one because it adapts itself slightly. I'm not 100% sure exactly how it do that, but I used it to have no leading zeros and so on. So I think it tried to adapt itself. But that's a bit tricky one to call use I0. Could try. Either open up an Emacs here on format. Yeah, it adapts itself. So you could 0 will behave more like free format.
Can we take a break for 15 minutes?
Yeah, it didn't require that. It didn't like that one. Yeah, we can take a break. Just cleaning up that one. So it didn't like that one. Free format and so to answer the I0 question is that it adapts itself. Yep.
Yeah. We can take.
So you can use I0 to adapt itself. So now we have a break.
Yeah.
I think it's time to start again.
Yes.
We'll continue with I/O to stored files, not only printing the terminal and keyboard, or writing from the keyboard and using the terminal. Yeah, I use 2, and as we heard, you could have problems with using the number 2. So if you have a runtime error or complaint, try something else like 17. 5 and 6 are reserved for keyboard and terminal. In C, 0, 1, and 2 are reserved. So be careful with those. But in C, you don't use numbers. You use you just get a file handle back from the process. That's also a number, but you normally don't care what that number is. You just use the variable file handle you get back. Anyway.
How about having a 2-digit number?
You can have 17.
Oh, yeah.
128. I don't know. I would expect that it's a normal default integer, which is a 4-byte integer. So you could, in principle, have 32,765. So 768 or 767. But I wouldn't count on it. It might be a limit somewhere. Yeah. So, yeah.
To me, I avoid the first single-digit numbers.
Maybe you could, but I've tried number 2 for years. But yeah, I totally agree. Avoid the 2-digit number. So
no, 1-digit number.
Yeah, one-digit number. Yeah, try start at 10 or something. Yeah, but you have to pick a number, and 17 is the most random number, so 17. Here I use 2, but it also works on Saga with 2, so well, I don't have time to change all the slides, but yeah. And then it can be done very simple. It can be as simple as just call open unit2 file equals myfile.txt and read from unit number 2, free format, and A. This is the simplest approach. There is no end to how complicated you can make it. For those of you who love Lewis Carroll, I could have done this in a much more complicated way, said the Queen, immensely proud. So there is no end to it, but we'll take the basic stuff. We have binary output, because the first one is reading, depending on what the variable A is. It could be, let's say that's a number. You enter 2 on the keyboard and it will be assigned the number 2 to the value 2 to the variable. But it's an also interesting thing that we can do binary output. Data structure can be written. You can, and then it's just writing the bits out to a file exactly the way that they are stored in memory. This is portable between identical machines, but it could make problems if you want to move these files around. So be a bit careful with that. Don't count on that binary files can be moved around, because they rely on the internal structure of the floating point system on each system. And since most of us are running x86 system from AMD or Intel, it actually works. But as soon as you try something else, like moving them to an ARM machine, it might be problems. So then you need to have some exchange formats. But unformatted files are extremely efficient, and they are very, very good because you just read in the bits, and you don't really care about byte. You just read the bits in, you read 64 of them, and you have a real 64 number, an 8-byte number. So here again, I open myfile.txt, which is a bit strange to calling it txt when it's unformatted, but I just copied from the former slide. And I write X, simple as that. I write out an array or a vector field, a matrix, 100 by 100, 64 bits reals, 10,000 of them in the variable X. And just I write X, and they are written. So then we explore this in another round of demos. We have text format that's called file IO write. You need to run the write before you can run the read, because the write writes out data, and the underscore R reads the data. And we'll go right at it. First, we take a look on the file. File IO write. It is easier to write than read. ISO Fortran, I said it file unit 2. Maybe if I change these to 17, it wouldn't matter, because these files are stored on my local computer and I upload them to Saga. We'll put in a file name. I hard coded it in here. Most of the times you will either read it from keyboard or get it from somewhere else, but here I just hard coded it in. I have a J, which is just to write some numbers, which I have a one single byte integer. This is something that I learned from programming tiny units like Arduinos and such, to only use the variable sizes you actually need. I open the file. I set the unit to file unit. I set the file to file name, and I set the action to write. So we are supposed to write to this file and not read, only write. So I use action write. There's a lot of things you can use to open the file. There's many, many options. Then we write 10 numbers to the file. And since there is only one number here, one integer, there will be a new line for each number written. So this file will contain 10 lines in ASCII format. So we can compile it. File IO _ W, and while that compiles, I'll close the door. In the old days, compiling could take a long time. Okay, what happened? You see, it took some time. It wasn't instant. That is because file access on Saga is a nightmare. Because there are many users and a lot of things going on, and not all programs behave nicely, and there's a lot of programs doing I/O. That is why bioinformatics and a lot of codes that are actually doing a lot of I/O are placed on Saga, but sometimes it can be very slow file system. And if people don't behave themselves and do stupid things, it can take 60 seconds to do a simple ls. But this is the way things are. I mean, the users they run their programs, and you can't expect all users to have full insight of computer hardware and so on. So this is a fact of life. So if you are plagued with slow disk access on Saga, just accept it. Just as you accept queues on the road, you have to accept queues on the I/O system on Saga. This is a fact of life. It's just cope with it.
Is it the time to say that we are running this course on login nodes, but we request everyone when they do actual calculation, submit a job?
Oh yeah, if you want to run something that takes more than half an hour or 15 minutes, do not run it on the login nodes. Do not run production on the login nodes. Yeah. But this is fine to run. This is what the login nodes are for. This is playing around, compiling programs, testing, unless they are large, because then we'll eat up, because there is a limited amount of memory on the login nodes. And if you have many users, then you run out of memory. No. So small things like this is excellent to run on the login nodes, but anything else that requires some resources, run a job. Anyway, we now have written 10 numbers to the file, and this will call my file. Data file, not my file. Data file.dta. DTA normally signifies a digital file, but it's a data file in. And as expected, 10 lines because each time you write a number, it will be followed by a new line, and we have 10 lines. Okay, so how do we read this in? Reading is more tricky because you don't really know what to expect. So you can see there's another one here. IO status. Then there's also a logical called present. And the file name and A and J. Okay, now we introduce another new concept. We call up the function built into the language, intrinsic function called inquire. It can do a lot of things. But in this case, we just ask to check if the file name is present. We call file equals file name, and then there is a keyword that you can give called exist, and we give it present, which is our IOs. Yeah, we exist present, which is the logical variable. So when this one returns exist, present, the variable present will either be true or false. So if not present, we print out file not found, and we call a function called exit, and we give it number 1 because this is an error. So we just exit the whole program, abort the whole program, because there's nothing we can do if the file does not exist. So this will happen if you run and compile the read before the write. So there is no file, or if you delete the file. So now we know that the file exists. We say open, but action read. Action read is important because there are a lot of people who can open the file for reading simultaneously, because it doesn't affect any other if you read the file. So the file system is very happy that you open a file with read, because it doesn't have to put a flag on it or a token. So if you open a file for write, you get a token. So the file system will prevent anyone else from opening the file for read while you have the token. But if it's read, there's an unlimited amount of tokens for read. And here we know that there are 10 numbers. In many cases, you know how many numbers to read. And see, I don't even care about testing whether or not there's an end of file or not. I just read because I expect 10 numbers. If there are not 10 numbers, something is wrong. So the program will abort, but that's okay anyway, because then something is terribly wrong and we should abort. But of course, it could be tested as much as you like. You could put in, there's no end to how many tests you can put in. But we know there are 10 numbers. We just checked it here. We see that there are 10 numbers, and we emit them. Then, yeah, we'll run this part and explain the later. Yes, fine. 10 numbers. 10 numbers are written in. So it works. File works. It works. Here, the file is still open. We haven't closed the file. So if we want to read it again, we use the statement called rewind, which is an interesting statement, because remember that Fortran is old and we used tape for many of the storage. Even very, very early on, tape was used for storing files. And then we just call the function rewind, which means rewind the tape. And then the read marker is positioned at the start of the file. So now we are in the position that we have rewind the file, which is equivalent to the state that it's in when it's open for the first time. But we don't know how many numbers there are in the file. Okay. We try reading. We try to read. We use the file unit, which is connected to the open file. We use free format. I said FMT equals star here. That's just equivalent to just put it in there. But I'm using another variable, so then I saw it nice to play it nicely and put in FMT. FMT equals star. And then I call IOStat into the IO status variable to check whether or not it went okay or not. And then we read in the J if there's something to read. So then we have the variable IO status, which is an integer up here. And we feed that into an intrinsic function called isIOStatEnd. We could check for IO status different from 0, because if everything is okay, we get 0. If there is end of file, we get something else. But I thought I might find it opportunity to use the function isIOStatEnd, because it could be end of record. which is different, or it could be something else. So there is a few functions that you can test because this is related to the fact that the IO status number could be anything. This function know what that number mean. But if we use 1 here, it could be totally wrong on another compiler. So using this intrinsic logical function to test whether or not IO status is end is actually a very good idea, instead of just testing for different from 0. So this is more portable and safer. If that is the case, we call exit, and we learn from last time that exit here, which is a statement. It's not call exit. Call exit is calling a function, a subroutine called exit with number 1, which is exit the whole program. Using the statement exit the do loop. Otherwise, you will be no way of getting out of the do loop because this is an infinite loop. So if IOStat becomes end, the IO status gives this function true, we exit the loop, and we place ourselves here, and we close the file, and we're done. So this is what happened here. We read in 10 numbers. Because when we have read 10 numbers, the IO status, next time we try to read the 11th number, this one will signify that there's something wrong. We have reached the end of the file, or we are read out of the file marker. Try to read beyond the file marker end, the end of file marker. And then this one is true because we have reached the end of the file. We exit the loop and we get to the close statement and we end the program, which is exactly what happened here. Cool. This is text file. Now we can try with the binary file. Binary file. It's fairly small. Implicit none. I use file unit 2. We have to change this to 17 now. Doesn't matter because on Saga they are still 2. It doesn't matter. Here we also have a data file, DTA. We call into existence or declare a matrix or a vector of 2 dimension. 10,000 1,000 by 1,000 is a 10,000 numbers. They are of real 64, so they are 8 bytes. So they are 1,000 by 1,000 by 8 bytes in total. We call the random number generator. This is not mine, so it do not return 17 to all of them. But this is an interesting thing. We are feeding. Now I'm proceeding in this later today. We are talking about the vector functions, vector in syntax. We are feeding a matrix into a random number generator. But that's okay. Fortran can do this. This is related to the vector syntax. So you can feed a number in, which is a matrix. It will be okay. All these numbers will be set by the random number generator. Now you can speculate, is it called one random number, so they all entries on the matrix will have the same number, or it will be filled with 10,000 different numbers? That's an exercise for you to find out. I print out the 10 first element. This is again vector syntax we'll cover later on, but it will take the first column of the matrix, the 10 first numbers of line 1. Then I take the sum of the whole matrix just to show you that you can use the built-in function sum to take the sum of the matrix. I open the file, file unit, file name, format now is unformatted. Raw, unformatted, the bits are written exactly as they are stored in memory. Action, write. We write, then we just write the matrix in one go. Write file unit A, the whole matrix is written out in one single statement. No loops, no whatsoever. a whole matrix written out. Written binary data to a file. Cool. The first one answers the question that there are some numbers are not all the same. Then we have written, then how big is the .7 megabytes. It's the size of this file. It's not very big, but it's a sizable file. So how do we read in such a beast? Here we check if the file exists, same as before. We open the file, format, unformatted, action read. We check for status, but this time we know that A is the same size, since now we have to make sure that the sizes match up, otherwise it would be a bit tricky. So here I just checked for any kind of errors. Everything else than 0 is an error. So I print out error and then the actual number here. What that actually means, you have to look up on the table in the manual of the compiler. I read the binary file. I print out the 10 first elements of the first column, print out the sum, just to check that it was read okay, and then close the file. And they seem to be quite nice. Looks similar. That's why the sum is a nice one. It's a kind of checksum. So now I'll leave you to it a little bit to play with them. No, we'll take the name list before we set aside time to play with it. Name list is another one that is nice. This is a Fortran 90 code, A and B, X, so and so, X and Z, some character variables, some string variables, and this is variables used in the program. And we'll take a look on the name list. Since this is file IO, I thought we put it in a lump it together, and then we set aside more time for you to test them. A name list program, very simple one, but it's a nice concept. It's old. It was already introduced in the 77 standard. I declare some variables. First of all, I have a format. I declare some variables, A and B, a 2x2 matrix of integers. I make a vector X, Y, and Z of length 2. So this is a small vector. And then I have some character variables, land, sea, air, and soil. Then I use something new here. I called in the keyword called name list. I call it my data, start and end by slash. I list the variables I want to have. Then I print, make a format so I can print my data. Then I set the data, set A to 0. The whole matrix is set, every element is set to 0. B is set to 1, all elements, the 4 elements. X, Y, and Z, I said 1 and 2. You see, this square brackets, they are part of 2008 standard. They do not work on 2003. They are 2008. So be careful. Maybe they even newer. Since they work here, they are at least 2008. Then I take square all the y elements are set to x times 2, and all the z elements is y times 5, element by element. This is important. Any vector thing are element by element. I set the land, sea, and so on. I open the file. File is called namelist and MN namelist extension. Status is unknown. I don't know if this file exists or not. I call write. And there's a different thing what you can do. If the file do exist, what do I do? Overwrite? Or do I not overwrite? This is something you can do on the, you do inquire, or you can set it here in the what to do, whether or not the file exists. You could see known or unknown or exist, and so on. You have to read the manual to learn more about the open statement. Then I write my data, close the file, and print out files that are written to the file. So data written to the file. This is the variables for the numericals. You see here, I have the format are here for the numericals. Then I emit a new line. Then I take 4 strings. Numericals, 4 strings. Of course, you see there are a lot of space here, blanks. That's because these have 20 length, and I did not put in the trim. Then we clear the data. We set everything to none or 0, just to make sure that everything is cleared before we read the data in. Then I have closed the file, so we have to open it again. Then I read the data and print them. So now we have cleared the data, and we try to read them in again to see if we get the same. Yes, we do. Then there's an interesting thing here, because these are the data as they were stored. But does the sequence matter? Can we read such a file? This is the next one. Yes, they look the same. You see here they are blank, so we know that there's nothing here. So these data here must come from the red file, and clay, dry, North Sea, and the numbers are the same. Cool. So then we have another one. There should be a name list missing. We'll just copy it over. We'll see. Since the name list, you see, now there are 2 text variables that are missing. So what happened now if I only have a few of the data needed? What will happen? I've cleared the data, so there is nothing there. So what happens if I come to the last one? You see that the numericals were there. The only thing that was missing were the sea and air. Yeah. So the soil and the name and the country, they are there, but the others were not happened. But there were no errors. So if you have a data containing missing, you will not get an error. You will only update the one with name. So it maps name, the variable map for the label of the variable. So the variable map to the label in the file, which is a very powerful construction. So I'll leave you for maybe, how much do we say? 10 minutes, Tanya, for testing
Yes.
this, or
Yeah.
more?
Yeah, we can give like 12 minutes.
Okay, continue a little bit,
Okay.
because
Yeah.
there is still something to cover, but
Yeah.
I think I'll start again now. It's more or less 10
Yeah.
past. It's very close. It is 10 past now. Yeah. I just wanted to touch briefly upon another thing that is new. I didn't know where to put it, so I took it out here. You can make your own variables, derived types. You can make a new variable type. I made it something that it's similar to complex numbers, because you can actually use complex numbers to pinpoint your location, because you can say that the real part is the north-south and the imaginary part is the east-west, and then hide both things in a complex number. Like the first time I came across a complex index of refraction, that was a bit tricky for me, because I know perfectly well what index of refraction is, but I never heard about a complex index of refraction. And because I'm a chemist, so I know that the physicists, they don't care. They have no restraint of what they can do. So they took a complex number. In the real part, they put in the refractive index, but on the imaginary part, they put in a damping coefficient, so that they use an exponential function and use the damping factor in the. So they put in two numbers into one variable, which is exactly the thing I've done here. I declare a type. I start with T underscore, because this is quite common. And it's called T underscore location, which is the type. It contains two numbers, latitude and longitude, and that's it. I have an example that we can go through. Here, this is just a short little demo about the location. It's very simple. I declare type T underscore location as a type. Then that contains two numbers, latitude and longitude. I declare a variable called location as the type T location. Then I use the Fortran 2008 syntax. I use the percentage, which I set location latitude to 60 and location longitude to 11, and print out the location. Then you can set it a different way. You can set T location, but you have to, in order to assign location to these numbers, you need to specify the type. And then you can, here 20 is the latitude and 120 is the longitude, because the first and second variable. But if you want to shuffle around the variables, you need to name them. So you can set your location to longitude 30 and latitude -80. And then your task when you have ample time is to print the location in decimal degrees, minutes with 2 decimals, and use the northwest, north-south, and east-west indexing. This is a nice exercise to play around with variable things and conversion. Location is also as expected. I mean, this is nothing special with this. So, yeah. And you can imagine that there is no end to how complex variables you can make. So this is just a very, very simple example. So we'll dive deeper into this, but I thought it might be interesting to show while on day 2, because it's going to be becoming more apparent later on. It's related slightly to the vector syntax. You just been shown a little bit of what the vector sizes can do with the random number example. But with the 90 standard it was released a little bit later than 1990. You could have vector syntax. And there was also a bit stricter declaration of indexed variables, often referred to as vector or multi-dimensions of vectors. You can have up to 15 dimensions in the 2008 standard. So the keyword is dimension. Declare vectors of different dimensions and sizes. Integer dimension 100, which is a single vector in 1 dimension. And with logical 5 elements. Real 64, 10 by 10, 100 elements. 10 by 10 by 10, 1,000 elements. Complex, which is an interesting one. A 10 by 10 by 10 called Z. Or a complex in 32-bit variables in 4 dimensions, which is all of them are set to 1.4 on the real part and 1.5 on the imaginary part. So again, this initialization of W is also vector syntax. You couldn't do that before. So say farewell or to most of the do loops. In normal circumstances, you will lead some do loops, but a lot of things you can do with the vector syntax. I used capital letters here because signifying that they could be, let's say, matrices or vectors or matrices. I set all elements of matrix A to 0. I set all elements in A to the element by element sum of B and C. So A11 will be set to B11 plus C11, etc., until you get to NN on both of them. Then I said B equal B times 10. That means that every element of the B matrix will be multiplied by 10. Same goes for the C matrix. And all elements in the C matrix will be multiplied by itself, raised to the power of 2. And you can easily imagine that if you have a multidimensional field or vector or whatever, let's say if you have 15 dimensions, that will be 15 do loops in the 1977 standard, and 15 continues later on. Well, you could get away with 1 continue, but you will have a lot of do loops. And as we heard about on the first day 1, that many codes contain a lot of do loops in different dimensions to signify the coordinates on the globe, for instance, and the height, that are 3 dimensions. Some of these you could get away with by using the vector syntax. But the most important element or message to take home here is that it's element by element. So A equals B times C will not be matrix multiplication. It's element by element. So assume the B and C and arrays, and B plus C is equivalent to, so I see the do loop. So more or less the same as I said before. And but A times B is different from matrix-matrix multiplication. It is element by element. If you want to do matrix-matrix multiplication, you have to call some functions or some external libraries and so on, because it's not the real matrix-matrix multiplication or vector multiplications, or they are element by element. So all of this you can get away with the Doodle. There are a lot of exercises, but we'll go only through part of it. Otherwise, the other ones are a bit complicated, and there is not really time to go through because it's regarded as advanced Fortran, because there's a lot of things we can do here, a lot of tricks. Assigning, extracting. Assume that A is a vector of length something. I want to have element 1 and 2. Extract. I want to slice or extract element 1 to 2, but every second element. That won't give us very many, because the first and the second, that will give us, if it was a long vector, if the 2 in the third one was 10, that will give us the first, the third, the fifth, etc. But this one gives only 1 because it's length 2. And shaping, it's to set up the vector. Here is 1 to 4. Reshape, we can have a vector 1 through 4 and reshape it into a two-dimensional vector, a 2 by 2. Then we can have a mask. We can set the vector L to every element of vector L will be set to the test of vector A, one element by element. So all elements in L will be the outcome of the test, elementary test of L less than 0. No, A less than 0. So there are some exercises or some demos. I'll go through them. There are some advanced usage that you can take as homework and an exercise to understand. It's called slicing.f90 and pack.f90. And the real challenge, where I advise you to have ample time and sit down with paper and pencil and review the quicksort example. I left that as a challenge because it's elegant, but far from trivial to understand. But it shows how you can actually use these functions that you learn from slicing and packing in an elegant way. And I'm really not sure if that's the right way of programming, so that you have to spend an afternoon with paper and pencil to understand what's going on. Maybe it's better to write it for children and journalists, so normal users can actually understand your code. But it's an interesting example, but we'll not cover that one. We'll cover the vectors 1, 2, 3, and 4, and then we'll continue. So vectors 1, I declare a single vector, a parameter n equals 3, and I declare a vector of 1 dimension A and another vector of dimension 2. Then I print out the size of the vector, which is the number of elements in the vector. This one is an interesting thing, because this number here, size of the vector, you can use in a do loop. You can say do I equals 1, comma, size of the vector. So you can get the size of your vector if you want to use it with a do loop, instead of having to pull this n as parameters to your functions and subroutine, or using through the whole program. You can use size of A as the end index of the do loop. And then I take size of B, and then I took size of B, but only the slices 1 to 2 and 2 to 3, and took the size of that one. Then I assigned 2 to all elements of A. I assigned 3 to all elements of B, Remember that A was a one-dimensional, B was a two-dimensional, but that doesn't matter. We can assign as we like. Then we extract two first numbers of A. We extract every second element. And we extract part of the 2x2 matrix. Can we print the matrix? I thought I could show how simple it can be done. Very often it's done with an implied do loops and so on. So I've also used that, but this one is the simplest way we can do. We print it by relying on the fact that when you have printed three integers, there is a new line emitted. So it looks nice. Same goes for this one, because this is only a 2x2 matrix by now. Even though B is a 3x3, we have only extracted a 2x2 out of it. So we try to run it. Vectors. We'll see that size A is 3. 3x3 is 9. Here we extract only the 2x2 matrix from the 3x3 matrix, and we arrive at 4. We print some data. A. We print it just like without any formatting. We arrive at 9 numbers. We extract the two first elements of A. We extract elements from A, 1 and 2 by only the second one, and we arrive at only 1. Then we ask for a 2x2 part of B, and we get 4 numbers. Print the matrix. The simplest way of printing the matrix, 3x3, all of them are 3. I could put random numbers in, but I didn't. Then we extract only the submatrix, and we arrive at 3 times 3. This is the real beauty of this language, the vector syntax. This is different from C and all the other. This is where Fortran really stands out for doing mathematical operations or data operations at all, shuffling data around, slicing, packing, moving, calculating, anything related to mathematical operations. Here it's where it shines, and performance-wise, likewise. So this is why the language has been surviving since the 50s. You remember, it's called formula translation, and the language has been updated more and more. And there are more and more of these things, but the vector syntax was a milestone when it was introduced in the early 90s. So what's happened if we go to vector 2? What do I've been boiled up for you here? Few things are the same. But now it's a real 32, real 64, and real 64. We have a one-dimensional one, two-dimensional, and three-dimensional. Again, the size I assign, but since this one would be okay without real 32, because the default value is real 32. But here I need to tell them that this text, this constant here, is of type real 64. And this constant is of the type real 64. Otherwise, it will complain that I'm assigning an 8-byte integer with a 4-byte integer, and that's not really good. So I get a warning. Or you could use some intrinsic function to convert a float to a double. Anyway, we print out, and remember that Fortran is column major. So the first column, if you start indexing a matrix, the first column is the one that comes contiguous in memory. So you should always run the innermost variable should always be the first. So colon is a wildcard, meaning all entries. So A column, all of them. And here, the first one for the B, which is an 2x2, or which is an n by n. So B is the first column of the first and row 1. And likewise here, the first column. The other ones are set to 1. Then we assign the first column. I say line, column. Assign only line 1. Yeah, assign only the column for line 1. Yeah. So now we can vectors 2. We get 3, 9, 27. 3 by 3 by 3 is 27, so that's fine. We print one vector. 2, 2, 2. B, 3, 3, 3. It's all, yeah. And 7.75. Yes. We can print up only one vector by this syntax. Then we set the first one to 0.2 and the second one to 0.2. So we see that columns of line 1 are all set to 0.2. And likewise 1 to 3. 0.2, 0.6, 3. It's not changed. And then we set some more numbers here, 0.2, 0.2, 0.2, 0.6, 0.6, 0.6, and line 1. 1, 1, 1, 2, and 3, 1. This one is a bit tricky. You have to sit down and see what's happening, which column and which row and so on. You just have to sit down and yeah. And then we have more formatting. This is also an example of vector syntax again. I say A equals the square root of A. I print out A and what that comes to, the whole vector. B equals the logarithm of B. Print out that one. C equals the sine of C. I print out a few of those. And we can see what we arrive at. A, the square root of 2 is 1.4142, so that's fine. The logarithm is okay. You take the log. And C, we take the sinus, which is 0.78. And we can print out C in a slightly different way because it's 3-dimensional. I'm not sure how to do it, so it's going to take the 3 by 3 here and stack on top of this and stack on top of this, so they will be stacked in a cube. But it's not so easy to print a cube, so this is one way of doing it, printing out the layers one by one instead of printing it as a cube. It could be an interesting one to make a graphical program that you could hide the numbers like in a semi-transparent cube and put the numbers in there and you can rotate it. It's a nice thing. So this is more about vector syntax and manipulations and slicing and so on vectors. Then we have the vectors 3. Here I've gone haywire with the initialization to show that you can init vectors and such. I've declared some here. They are fairly simple. They have not been assigned to anything. But here I start assigning things. The E echo is 4 length, so I used the square brackets and assigned it to 4 numbers. I put in integer here and put them into real 32. This should probably be dot behind the number, but it's okay. It will assign them as real, even if they are integer here. Then I assigned I from n divided by 2, because I have said that the dimension here is n divided by 2. 10 is divisible by 2, so it's 5. But it will be rounded to the closest integers. But be careful with such constructs. So make sure this is an even number, not to make problems for yourself. And then I just assigned it to the simple numbers 1 through 5. Same here, but here I said prove the point that in an implied do loop you can call functions also. So I said logarithm to real. A logarithm can only take in floating point numbers. So I said logarithm to real of I, that converts the integer to a floating point number that fed into the logarithm, and the outcome of this is in this parenthesis, and those vectors are, those numbers are put in a vector assigned to G. And then I have 1 minus 5 to plus 5 and just a simple number. Then I have a complex one, same again. I use the same as before. Then I put up some dimensions that we all know, sizes that we already know, but I also call for the called shape, because shape is, for this one it will be 1, but for B it will be 2, etc., etc. It will be 2 by 2 for the other one. It will show the shape of the vector. And then we can print out some stuff. You see the A 10, 100, 1,000, and D is 100. H is 11, because 11 goes from minus 5 to plus 5. That's 11. 5 by 5 by 5 by 5 is 625, because 5 by 5 is 25, and 25 by 25 is 625. So that's match. That goes. That's fine. And then shape of A, 10. It has a vector of length 10. B is 10 by 10. C is 10 by 10 by 10. Shape of this one is 10, 5, and 2. And yes, 10, 5, and 2. 10 divided by 4 is rounded to 2. And the H was minus 5 to plus 5, which is 11, and 5 by 5 by 5. Yeah. Then we print out some element, but this is just an exercise in formatting, so it's not the most interesting thing. The interesting here is that you can get the real elements and the imaginary part by the percentage. And of course the vector syntax to print out the last one, which is 5 numbers. So this is typically something that you need to sit down and play, because when you see it, okay, this is not the most difficult thing to understand, but to have it in your fingers and to know it, you really have to play with it and learn it by muscle memory, as the English call it. We'll go through number 4. This is masking. I have also NLIC 10. I have an integer vector A, and 2 of them, vector A and B. Then I have a vector of floats, 5. And I assign the A vector to some numbers here, and all B elements to 0. Then I print it, and see what's happening. Then I do something strange here. I take the vector b and set it to the outcome of the function called pack. Pack is a very powerful function. It takes some vector element or some multidimensional variable, and the next one is a mask. So for all elements that are greater than 0 will be put into vector b. So only assign aj to bj where aj is larger than 0. So we can take the first one. A. This is vector A. We know that all elements of B are 0. So we assign B with those elements of A that are greater than 0, which are those elements are input to the vector here. Then we use a new construct in Fortran called where. It's very, very powerful function for vector operations. We say that where A is less or equal to 1, B equals A. So for all elements of A that are less than or equal to 1 are put into B. So we print B again. We arrive at these ones. Less or equal than 1, that means all the negative numbers, 0 and 1. The others are not affected, so they are still 0. Then we want to take the square root of vector x. Vector x contains negative numbers, and unless we do something fancy, we cannot take the square root of negative numbers. So we need to mask out all the negative numbers. So we use where x is greater or equal to 0, we take the square root of 0. And elsewhere, we just flip the sign of x. So we make it positive, and then we get a square. We can take the square root anyway, because we know that these are negative, and flipping the sign gives it the positive number, and we can take the square root. Of course, this is it's just an example. So print it, and you see you get it printed out. Square root of 3 is 1.7, 9 is 3, 2 and 4 is 2. So we now covered the vector functions or vector syntax as an introduction. There are a lot of things, and since we have only limited time left, I think that these are a bit complicated. So I think this is better spent doing because if you set out 10 minutes to play around with this, you won't really manage to do more than understanding the first one. I can only show you the slide. Slicing, which is for the advanced training. I have a vector, I reshape it into 6, 6. I start a matrix, I take the diagonal, I take the combining elements, I merge them, I squeeze and manipulate and so on. I take the product, I take the mean and maximum. And so spend some time reading this. Here I use mostly implied do loops to print. You could adapt into the other way of doing it. Then we have the pack, which is even more. Here I also do allocate, which we are not covering today, but that's the next time. Then I print out a lot of package stuff with masking, masking in a variable and so on, size of tree unknown as compiler make, yeah. So there is a lot of things to learn when it comes to the vector syntax, but this one pack here is regarded as advanced, so it's no time to cover it here, but I think you should have seen this, and the QSort will skip. If you like it, you can play with it. And the only thing I would like to show you with the QSort is that Fortran QSort dot capital F. Capital F is important here. If I build it like this, the program runs. So this is fine. But if so here now comes the need for capital F. If I feed the flag called debug, the preprocessor will make sure that the debug flag is honored and compile likewise. So now we get a whole bunch of output. So this is a nice construct. You can review the code and see what's going on with the debug flag. But this one is using construct like this can be of importance. Yeah, I can show you the code. It's here. I did not write this myself. That's why it's the disclaimer here. If def debug. If debug is present, it will print out this. So this is left for self-study and exercise, but it's a nice way of understanding what's happening. The pack function and the slicing, you should try to spend time understanding what's going on. Otherwise, you'll just look on the vector examples. But it could be nice to see that there are functions that can do so many strange things for you, since they are operating on index fields and vectors and such. So then we can scan through this.
Or should we take a break, Ole?
Yeah, we can take a break, but we'll just skip through it because this is already covered.
Okay,
so a couple of minutes more.
Yeah.
You see modern Fortran mask that we covered in Fortran 77. It's not, it's even worse because you have to know the N. So N has to be propagated through subroutines and so on. You always have to carry with you the N. With modern Fortran, you don't. You can, if you not using the vector syntax, you can query it by the size. So we have the shape and reshape and pack. Those are dealt with in the more advanced examples. But it's possible to reshape a vector from change it from a long 1D vector into a 3x3. It's an n by n, or a 2D matrix. You can squeeze and pack, and there is actually no end to what you can do. So if you want to learn more, you can review a couple of examples and then start reading the book, because there are so much nice things you can do. So those we already covered. Then we're actually done with most of the things today. So that's why I thought it would be beneficial to have a break and then have a Q&A and so on for after 12. What do you think of that?
It would be great. I have a question to raise. There was this question number 8. Implied do loop is like the list comprehension in Python. I was not sure if it exactly replaces that.
I don't know. I'm not really sure. So I don't really want to answer it because I might be stepping on thin ice here.
Okay.
I know I do program in Python, but I'm not that good in Python.
And I'm also not very
but I
well
can show another interesting example that I regarding to the format. I did not put it in as an exercise, but I put in a demo demo for formatting. I remember I wrote this in Python for my daughter because she had Python at the videregående. So multiplication table. This is nothing fancy with this. You see here I actually pull in a new line and using an implied do loop and so on. So yeah, this is the whole multiplication table. But then I thought that I should raise the bar a little bit, because if you all know the Roman numbers, so a challenge is to multiply 9 by 11 in Roman numbers without translating to our 10 decimal system. That's not so simple. And then I remember that they used to have boards in ancient times where they have the Roman numericals and their multiplication. So they had a multiplication table on a board on a big table. And of course, in Italian, a table is banca. And if people were cheating by making a false table, then at that time the police and tax inspectors would come and smash your table, breaking it to pieces. And also from Latin and Italian, rapta, which is mean destroying. So bancarapta, which is mean destroying your calculation table. And that is the root of the today's things called bankrupt. Bancarapta. So this was, I raised the bar a little bit to do this, to make it in Roman numbers. So here I also use a function that we'll cover next time. I have a decimal to Roman function that actually make Roman numbers. So this is also an interesting thing in formatting, but it's not really something that they expect you to learn, but it's an interesting exercise in watching how format can be done.
Yeah, and I have uploaded these files also on the repo and Google Drive, so you should have this. Okay, and I see Maikin says that the list comprehension and implied do loop are similar way, work in similar way.
Yeah.
So that's great. Yeah, we have someone who knows that.
So here are the multiplication table in Roman numbers. So it's an interesting exercise about looking into the format. Forget about the functions and so on. It's a bit tricky, but it's an intellectual exercise to understand how it's working. But this is easy. The quick sort is not. It took me some time to with paper and pencil and some debug to actually understand what's going on.
Yeah, shall we
So we
take
take a little break and we take a Q&A after some time.
Yeah, 5 past 12, we will have a break.
Yep.
And thank you, Ole.